And hello everyone, welcome back to this discussion on the kOmega SST model in this turbulence modeling series. The last video, we generally tried to describe this blending function, which is F2. Okay, here, this blending function, or rather F1 rather. Yeah, we described the behavior of this blending function. And basically this helps us to blend both the K epsilon and the K omega model. Okay, so that K epsilon model will activate in the bulk region of the fluid where turbulence is dominant, and the K omega model will activate during in the boundary layers. Okay, so that you can see this extra term from the K epsilon model. This will activate in the bulk region, and of course the constants between both of them. All right. So for example, alpha here will be a blend of alpha from the K omega model, and then alpha from the K epsilon model. All right. So likewise, the same is done for beta over here. A beta from the K omega model and beta from the K epsilon model. Alright, same goes for sigma K and omega, sigma omega. So these two constants. Okay, so in summary, the constants are blended between the K omega and K epsilon model in this K omega SST model, and of course you have this extra term popping out. Okay, so this is what we call the baseline model, K Omega BST or BSL rather. Okay, so this is like the precursor to the K Omega SST or K Omega shear stress transport equation. So even with this blending, there are a few problems that pop up. Okay, the first problem is that experimental data shows over-prediction of Reynolds shear stress in adverse pressure gradient flows. This is from the 1994 version of the K Omega model, K Omega SST model, and this is Menter's paper for the K Omega SST. Alright, so this is one of the problems that happens. Question is, what are adverse pressure gradient flows? Now the Wikipedia is here for you to read. If not, I can just roughly show you what it is. Okay, so I will have this paint down here, make it a dark color, and I will, well, okay, let's say this is what we are normally used to dealing with, a flat plate boundary layer where you have some free stream velocity. Okay, maybe I will use a straight line here. Okay, straight line here. And idea is that, okay, boundary layer will start to form here, and then you have a turbulent transition region, okay, after a certain length. And the idea is this, okay, over here you'll have all your wall functions. All right, you will have your wall okay, it should be here. Yeah, you'll have your wall functions with this. All right, wall functions. Okay, and generally you try to have it such that if, okay, this is free stream flow. If you have pipe flow with some average U, you will have a turbulent sublayer here, or some boundary layer here, and then here you have the bulk flow. Okay, so if this is a pipe flow, for example, normally your pressure as you go from, let's say here, the left to the right, okay, and this is X, so usually dP dx is less than 0, right? dP dx is less than 0, meaning to say as your fluid travels from here to here, you will experience a pressure drop. Okay, so this is normal, like pressure driven flow, the normal flow we are used to. Okay, and this is also some sort of semblance of normal flow. Okay, so over here in the flat plate flow situation, dp dx we can neglect. Okay, you can neglect or just set it to 0. Okay, that's usually the case here. There's no pressure gradient driving this whole thing, and this is the assumption for boundary layer. For boundary layer, wall function. Alright. Okay. Okay, problem is, okay, what we talk about is adverse pressure gradients. So what are adverse pressure gradients? Adverse pressure gradient okay, so let's say you have some flow. The general idea is that you have some finite flow with a velocity going here, and let's say this is increasing x. Well, adverse pressure gradient means that dp dx is actually more than 0. That means as you travel down the pipe, the pipe pressure, the fluid pressure increases. Fluid pressure increases. Now, where do you see this happening? Now, usually, let's say you have a sphere here, and then you have some free stream velocity. As you kind of approach the sphere, there will be some sort of like direction change of the velocity, and over here, especially over here, okay, pressure starts to build up. Okay, pressure starts to build up over here. Alright, and also if you notice this part anyway, then if you see this part, and then we will have a curve of sorts. You'll have boundary layers like that. Okay, and as you go down, okay, somewhere down the line here, the velocity starts to become 0, and then further down, okay, the velocity becomes less than 0. That means that the fluid is traveling in the reverse direction. Now this is known as flow separation. Okay, so in a flow separation scenario, we will have adverse pressure gradients. That means the del P, del X, if you consider X to be like this direction, del P del X is more than 0. Okay, so if you take a look at the Wikipedia thing for this, okay, in fluid dynamics, an adverse pressure gradient occurs when static pressure increases in direction of the flow. So that is the idea here. Okay. So if you see the Wikipedia pages, this is just an example. Adverse pressure gradient is very closely related to flow separation. You can see here. When you look at the Wikipedia page for flow separation, you'll immediately have to talk about adverse pressure gradients. So I mean this is what adverse pressure gradients are talking about here. Now what's the problem with the kOmega SST? Okay, so experimental data shows that the Reynolds shear stress in adverse pressure gradient flows as over predicted. What does that mean? It means that in regions such as this, the Reynolds shear stress, so the tau turbulent, for example, so that's the UIUJ prime, this is overestimated. It's overestimated here in such regions. Okay, that's what's happening. So we got to come and think of a way of how to deal with this problem. Okay, so so when dp/dx does not favor flow direction, that's called adverse pressure gradient. That's what we've talked with just now. That means dp/dx should decrease with the flow direction. So this is something we haven't dealt with in previous flows, but for curved surfaces, like I said, the airfoil and spheres, this doesn't work as well. So how do we sort this out? So in the 1994 paper, we find a key assumption called the Bradshaw assumption. So in that, because if you use the normal kOmega SST, this will be overestimated. But based on experimental data, and also, yeah, this is not exactly experimental data, but it's validated by experimental data. So it's a validated assumption. Okay, tau turbulent equals to some constant into the turbulent kinetic energy. Okay, so this is known as Bradshaw assumption. Okay, let's try getting this neater. Bradshaw assumption. Okay, so to prevent this term from getting excessively big, we apply this in the boundary layer. With adverse pressure gradient. Okay, so this is the general idea behind dealing with this problem. Okay, so like I said before, the Bradshaw assumption says that the turbulent shear stress will be equals to the density times some constant into the turbulent kinetic energy. Okay, so how do we actually calculate Reynolds shear stress normally in the kOmega baseline model, or the baseline blended model between kOmega and K epsilon? So this is normally how we calculate the Reynolds shear stress, where the turbulent shear stress is the dynamic viscosity, or the density into the kinematic viscosity, times some strain rate, which is du dy. Alright, this is the most simple one. Okay, so du dy is otherwise known as the rate of strain, S. So sometimes it's known as omega in the original papers, but I mean there's some differences between this, but I'm not going to go into that here. Okay, so so if we want to compare this term to this, we can rewrite this whole equation here, in terms of turbulent kinetic energy. So if we were to rewrite this in terms of turbulent kinetic energy, I'm not going to show it here because it's going to be a long derivation, then we will have something like this. Tau turbulent equals to the square root of production of K over the dissipation of K times rho 1 alpha K, rho A1 into K. This is from the Menter 1994 paper, and it's like this. And however, if you want to compare it to the Bradshaw assumption, you can see that this extra term here pops up if we were to use this form of the turbulent shear stress, the Reynolds shear stress. So ideally, this term here should be equals to 1 in the boundary layer. Alright, so this extra term actually pops out, so I just highlight this. Okay, this extra term pop up, and ideally this should be 1 in the boundary layer so as to satisfy this. Okay, so to be true, this production of K over the dissipation of K should be 1 inside the boundary layer. Okay, especially those with adverse pressure gradients. Unfortunately, in the K Omega baseline model, this doesn't hold true. In fact, this factor I'm highlighting in yellow usually tends to exceed 1 by like a lot. Okay, so the production rate of turbulent kinetic energy is greater than the dissipation rate of turbulent kinetic energy. So we need to, the idea behind this to curb this problem is again doing some artificial forcing. So we have yet another blending function again, alright, so that we have this inside the boundary layer, especially those with adverse pressure gradients in the boundary layer, and then this you have this assumption inside like the rest of the flow. In other words, we need to resort again to blending functions. So the idea is you have the blending function tau turbulent equals to some blending function times this, and then 1 minus that blending function like this. So if we were to name that blending function arbitrarily, we were to just randomly name this blending function z, we might get an equation like this. So let's call a new blending function called z. Tau turbulent equals to z into rho a1k to 1 minus d rho nu t du dy. Okay, so this is similar to F1, so that we can try, similar to F1 in that we try to have z, okay, let's say we have our sphere problem. Alright, in the rest of the flow, z equals to 0, and in the places where you have this problem, z equals to 1, so as to force a tau turbulent equals to rho, okay, rho k into a1. Okay, you want to force this relation to be here. So that's what your blending function essentially does. Okay, so normally in the K Omega baseline model, or the blending function we talked about before, they call it F1. But I won't use the blending function F2 because in this equation, because that's not what the blending function for this actually looks like. Okay, so the general idea is this, but a different form of the blending function is used. So Menter, in his K Omega SST model, he writes this. He writes that the tau turbulence will always be equals to rho times the turbulent viscosity times this du dy, which is the strain rate. Okay, strain rate. Okay, so what he does is to leave rho and du dy untouched. He will change the turbulent viscosity such that it will have sort of this effect. such that the tau turbulence will equals to the this term inside the bulk region and this term inside the boundary layers, especially those with adverse pressure gradient. So that's the idea. Nu T is in the free stream. In the free stream, we will have this. Okay, I think I typoed something there. So this, in the free stream, we will have our standard K Omega formulation of this turbulent viscosity. But in the boundary layer, we need it such that the turbulent viscosity equals to rho A1K. So to do that, to find the value of the turbulent viscosity that does that, we do some simple substitution. So we equate this turbulent viscosity, or rather this tau turbulence to be equals to this tau turbulence. So then we solve for nu T. So alright, let me get pinned. Tau turbulent in the turbulent layer equals to tau turbulent in the bulk layer. Alright, so tau turbulent in the turbulent layer, what is it? This is rho nu T du dy, oopsie, dy, and the tau in the bulk layer, that will be equals to rho K into A1. So we solve for nu T, and we just switch the terms around. We cancel these two, and then we just get A1K over du dy. And if we were to do that, yeah, something like that. So we equate both of them, so that this nu T will take on this value inside the turbulent sublayer or the boundary layer. So nu T equals this in the turbulent boundary layer, okay, or just the boundary layer in general. Okay, so if you were to substitute this nu T back into here, you will just get the tau turbulence equals to rho A1K. Alright, now for this blending function thing to be done, we do the following. Okay, Menter uses this formulation of nu T. Okay, nu T equals to A1K over A1 omega star, or in the bulk region, then F2 du dy inside the turbulent region. Okay, so this blending function F2 will help us to do this switch between the boundary layer and the free fluid. And F2 equals to the hyperbolic tangent of this function. And we saw something we saw these two terms pop up before. Alright, we saw these two terms pop up before. We already know the behavior of this maximum function is somewhat very big. This we call it argument, or inside the paper it's known as the argument. Alright, let me get, so it's argument. Alright, and then you have a y plus. Okay, this argument is very big inside the viscous sublayer and the turbulent layer. This one, okay, such that the hyperbolic tangent of the argument to the fourth power equals to 1 in the boundary layer. Okay, so this one was the F1 function. Okay, now F2 is slightly different. Instead of because this argument actually had one extra term here. Okay, this argument actually had one extra term which we don't consider here. If you remember, there's this 4 sigma omega blah 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 thing that we were spending lots of time dealing with, but this is missing from here, and this one seems to have a 2 in front of it. Yeah. Okay, so but anyhow, that's just a matter of constants. Okay, that's just a matter of constants. So yeah, that's but anyhow, the argument here is that, okay, you have a 2 here, doesn't really matter too much. The behavior is still more or less the same. It's just a matter of a matter of a scaling. Okay, it's just a matter of, you know, where does this start and where does this end. Okay, because anyway, yeah, the general shape is like that. Long story short. Okay, so you have a hyperbolic tangent, the argument to the squared. Okay, this one will be equal to 1 in boundary layer. Okay. Okay, if it's equal to 1 in the boundary layer, then f2 du dy is much greater than this, so that basically your nu t equals to a1k over this in the boundary layer. Other than that, when you increase the distance from the wall, f2 drops rapidly from 1 to 0, so that this over this a1k over a1 omega star, this will just give you the normal turbulent viscosity we are so used to. Alright, so again, f2 equals to 1 inside the boundary layer, and f2 equals to 0 inside the turbulent bulk, the free stream or the center of the pipe flow. Okay, so that the way this max function works is to turn on and turn off the turn on this formulation. Yeah, it'll turn on this formulation in the boundary layer, and then it'll be normal otherwise. So that's why you have a max function over here. Okay, all right, so that's how it's done. So f du dy is more than a1 omega in the turbulent sublayer. Of course, in the bulk flow it is the other way around, and this actually limits the production of Reynolds stresses, or yeah, it reduces the turbulent viscosity. It reduces the turbulent viscosity here artificially. It suppresses that inside the boundary layer. Alright, so if it reduces the turbulent viscosity artificially in the boundary layer, then it kind of reduces the production of turbulence in the boundary layer. Okay, so this modification is sometimes known as a production limiter. Okay, so nu t equals to this maximum blah 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 blah. Okay, that does what I just described in the last like 20 plus minutes. So of course in 3D you don't just have du dy, you need to generalize the coordinates. Yes, I'm oversimplifying, but it's just for understanding's sake. So the final form of this turbulent viscosity, or this production limiter, is this a1k over a1 omega star times f2 times s. I mean, not times f2 times s. Is the maximum of the product of f2 and s, so that you will have this equation right here, what I'm highlighting over here. Okay, yeah, so I'm not sure whether, yeah, I've got to check whether this 2 actually pops up, but it's just a matter of constants and fitting it to experimental data. So this is what the production limiter is about, and this is for the K Omega SST model. Okay, so but since you have this, you artificially suppress turbulent viscosity in the turbulent sublayer, you need to make some changes as well. What are these changes? Okay, so some of the constants. Okay, so Producing this change now produces a problem in the sublayer since we artificially suppress turbulent viscosity. So this is what I was talking about just now. This kind of upsets the balance of transport equations for K and omega, so we kind of need to modify them. What are the changes? Firstly, some of the constants have to be tweaked from the original K omega model. So if we were to compare these terms in the K omega model, for example, alpha 1 equals 5 over 9, beta 1 equals 3 over 40, sigma k1 equals to 0.85, sigma omega 1 equals 0.5. If you were to compare all these terms with the original K omega model constants, they might not always be the same. Alright. Reason is, okay, you may want to you have to account for this. So this production limiter. Alright, so one of the consequences is that you need to tweak the constants there to adjust for this. And the second thing is, I'm not going to go through in detail, but just get a rough idea. The other thing is that the production term of omega must be written in a certain way. So in the original K omega model, or the K omega baseline model, baseline shear stress transport model, the production of omega is equals to alpha 1 over nu t, tau ij, and then this strain rate over here. Okay, so since this turbulent, you can write the production term like that, given that nu t equals to k over omega star, right? If you still have nu t equals to k over omega star, you can still write your production term like that. So in the K omega baseline model, these two terms are kind of interchangeable. But in the shear stress transport model, nu t is not always equals to this term anymore, so we cannot use this formulation anymore inside the production term for omega. So to remove ambiguity, we write p omega, the production term of omega, as alpha into the strain rate squared, or alpha omega star over k tau ij, and then you'll have this strain rate here. Okay, so in most CFD guides, we won't see this problem because you hardly ever put the turbulent viscosity here. It's just alpha omega over k here, and I'm guessing they kind of remove that nuance to remove confusion for you. But this is one of the consequences that we got to be aware of, and this is actually stated in Menter's 1994 paper. So, alright, so nu t is removed from the expression in the K omega model inside this website here. So that's being taken care of, no problem. And this is the 1994 version of the K Omega SST model. Alright, so that kind of completes most of what you know for K Omega SST. But there are of course other updates to the model, and the problem too is dealing with stagnation regions. So there is another modification that comes for that, and I'll elaborate on that in the next video. So thanks for watching. If you found this video helpful, please leave a like and subscribe. Thank you for your support. Hey, bye.